Hi, my name is Jackson Muller, and I will be presenting our research into the Hoff transform and ground penetrating radar and how that can be used for wire detection. In this presentation, I'm going to be describing the problem that we face in the background. I then will be explaining the Hoff transform technique and how it can be used for wire detection, and then I'm going to share my results that we gained in our research. Since 1960, over 110 million landmines and other explosives have been planted in over 78 countries in the world. These explosives present a danger to not only military personnel, but civilians as well. It is estimated that 15 to 20,000 civilians are killed by these explosives every year. In the past, ground penetrating radar has proved very effective in detecting these mines for removal. The simplest method for detection is by the use of handheld devices, as shown in the bottom right. This method is very dangerous and inefficient as many lives are lost. The main device for detection right now is by vehicle and is very costly. Vehicles also have limited mobility. In our research, we are proposing that the use of drones is the best method.
Drones are more maneuverable than any of the other platforms. They are also the most cost-efficient device. The ground-penetrating radar can be attached to the bottom of the device, and the drone can be used to survey an area. These drones can be computerized to maintain a precise flight and maintain steady for the GPR to create a nice clear picture. Last, the drones are the safest platform because they don't have a chance to trigger any of the buried explosives. The modern threats we face today may not have as much metal content, or they could be buried deep in the ground. Also, the ground could contain other objects made of metal or other materials that could present a false alarm to the GPR. In our research, we will use the Hoff transform technique to process the GPR data and to detect the wires and their characteristics. The Hoff transform is a coordinate transform. It takes a data point xi, yi in the xy plane and maps it to a line in the AB plane. It then does this for all coordinates in the xy plane. It then uses a voting algorithm to determine a line. The lines in the AB plane intersect at a point AI, BI that determines the final line characteristics. The simplest form of the Hoff transform is by using the Cartesian coordinate plane as shown on the right.
In the Cartesian coordinate plane, a line is defined using the equation y equals ax plus b, where x and y are the variables. The Hoff transform solves the equations for the variables a and b, making x and y constants. It uses all the points in the xy plane to map to lines in the AB plane. The transform then calculates all the lines that intersect at a certain point. The point AB with the most intersecting lines gives the characteristics of the defined line. In the figures on the right, the Hoff transform is visualized. For example, the red point is located at x equals 3, y equals 4. In the AB space, this corresponds with a line with a slope of -3 and an intercept at b equals 4. The transform is then performed on the black, blue, and green points as well. When these lines are mapped, we can see that they all intercept at a point a equals -0.5 and b equals 5.5. This gives us the line shown in the first image, y equals -0.5x plus 5.5. The major flaw with the Cartesian coordinate system is the case of vertical lines. Since b increases to infinity, it is hard for the transform to map the x and y coordinates to the AB plane. Another form of the Hoff transform is by using the polar representation of a line. A line in the polar space is defined by two variables, rho and theta. To apply the Hoff transform to the polar coordinates, we need to convert the equation of the line in terms of the theta rho space. This is shown in the equation below. The transform takes a point, xy, and transforms it to the rho theta space as a curve. All similar lines are then found by using the binning similar to the Cartesian example. In the example shown, the same 4 points are plotted at the xy plane. Now, the red point corresponds with the cosine wave in the theta rho space. The point x equals 3, y equals 4 now transforms to the cosine wave rho equals 5 cosine of theta plus 53.13, using the equation shown below. As we did in the Cartesian coordinates, each of the points are transformed, and the intersection is calculated to be approximately rho equals 4.9 and theta equals 63.44 degrees, which corresponds to our line shown in the first image. Since both rho and theta are bounded and known, it is not as computationally complex. In our research, we will be using the polar representation.
There are certain steps that need to be taken before we can apply the Hopf transform to the data collected from our ground-penetrating radar. The steps include the projection from 3 to 2 dimensions, the clipping of low-level noise in the data, and the detection of the edge points. Then we can apply the Hopf transform and extract the line characteristics. The data we receive from the ground-penetrating radar is three-dimensional: cross-track versus down-track versus depth. The Hopf transform can only be applied to a two-dimensional image. So the first step we take is converting the three-dimensional data to three two-dimensional projections: cross-track versus down-track, cross-track versus depth, and down-track versus depth. Next, we must apply clipping to the three projections. The purpose of the clipping is to limit the edge points created by noise. Also, reducing the number of points will increase the speed of the Hopf transform. The low-level clipping sets all points below a certain threshold to 0 and then passes the points to an edge detection algorithm. In our research, we used the Canny edge detection algorithm. We chose the Canny algorithm because of its ability to filter out noise by means of a Gaussian filter. The algorithm determines the edges by examining the gradients of the image. This also speeds up the Hopf transform by eliminating even more points. The next step in our detection process is to send the edge points to the Hopf transform. It is applied in the polar Hopf space, as I mentioned earlier. For the Hopf transform, we define the discretization levels for the two line parameters rho and theta. In our research, the most accurate levels were 3 pixel units for rho and 0.5 degrees for the angle theta. The figure on the right shows the edge detected image in the Hopf transform. As you can see, the points from the edges are mapped to multiple lines. The color of the image represents the amount of intersecting lines, with the brighter colors representing more intersections. From the figure, we can see that theta is approximately negative 90 degrees and the rho is 70 about. The final component to the detection process is to extract the appropriate features from the voting of the Hopf transform. In our research, we proposed three features. The first feature is orientation, which is the theta where the maximum number of intersections occur. The second feature is the strength of the predicted line. The strength S is the counter value at the maximum of the voting map. The final feature we collect is the relative strength. We use this metric to lower the strength of the predicted line in extremely noisy data for the purpose of detecting false alarms. For our study, we used a step frequency GPR in copol configuration. It had a bandwidth of 6 GHz, and we used a spiral antenna on the GPR. Our dataset contained 9 total objects lying on the surface. Of these 9 objects, the first 6 are straight wires with different orientations and lengths. The last 3 are clusters of objects used as a false alarm case to compare with our wires. For our results, each object is illustrated by a set of 5 images. The first image we use is the surface view of the data collected from the ground-penetrating radar over the entire test region. The next image we use is a projected two-dimensional image of the cross-track versus down-track dimension after we applied low-level clipping. Our third image is the output of the Canny edge detection. The fourth image is the Hopf transform heat map in the polar space. And the last image we use is the Hopf transform represented in 3 dimensions, rho versus theta versus the number of votes. The first example we show here is a long wire case. The first image shows the location of all 9 objects. The horizontal wire is located toward the middle of the site and has little surrounding noise. Next, we project the wire into 2 dimensions where the line characteristics can be observed. In the second image, we can see that the wire is straight and should be a good candidate for the Hopf transform. The third image is the output of the Canny edge detector and shows the points that will be used in the Hopf transform.
The next image, the Hopf heat map, shows the curves associated with the wire points, where the brightness level is proportional to the number of votes. In the heat map, we can see the two areas where the heat map is bright, the first being negative 90 degrees and the second being at 90 degrees. The peaks of the Hopf transform are 180 degrees from each other, which correspond to the same line oriented in different directions. Last, we use the three-dimensional Hopf space to give us an illustration of the distribution of votes for the object. In the figure, we can see that the transform detects a strong line at negative 90 degrees, which is our horizontal line. The second example that we show is a cluster of objects on the edge of our test site. The object consists of a set of metal shrapnel on the ground. We can see that the metal creates a strong GPR response in our beamformed images. When we apply the Hopf transform to the edge points of the image, we see the votes are spread across many different rho and theta grids. As we see in the three-dimensional Hopf transform plot, there is no clear global maximum, and the maximum strength is low. It is only 14 compared to the strength of 71 shown by the horizontal wire before. Thus, the Hopf transform does not detect a single defined line for the cluster case. For the 9 objects in our test set, we recorded our 3 features in the table shown. As we can see, the relative strength provides us with a clear metric for our wire detection. For our first 6 objects, which are wires or have wire-like structure, the Hopf transform gives us a relative strength of over 0.25. For our cluster objects, the relative strength is much lower, around 0.1. If we were to set a threshold for wire detection, for example 0.2, we would be able to detect all of our desired wires while filtering out our false alarm cases. For this slide, I have included a graph to better visualize the relative strength of the wires versus the lower relative strength of the false alarm cases. In conclusion, we see that the drone-mounted ground-penetrating radar provides a steady image that is clear for use with the Hopf transform. We have found that the Hopf transform was effective in detecting wires with different orientations and different amounts of noise. We have also found that it is possible to set a threshold with our relative strength feature for the Hopf transform to only detect wires that we desire. In the future, we will be working on applying the features for wire detection using classifier. We will also look at how the Hopf transform performs with more noise and less edge points. With that, I would like to conclude my presentation. Thank you so much for listening. I look forward to hearing and answering your questions. Thank you.